So we are doing chapter 20, permutations, and we have defined permutations. We have defined composition of permutations, and we have defined some properties for the permutations. Then we have talked in the previous lecture about cycle notations and how we use them, and how important they are, and uh, then we have defined that every permutation in Sn can be expressed as a product of disjoint cycles. Then we have talked about how to count cycles. Now we will talk about the order of permutation, or you can say repeating a permutation. So you can say that the topic is order of a permutation. So let's say F is a cycle 1, 2, 3, 4, 5, and S5. Now, if you do F5 times, we send 1 all the way around back to 1. Similarly, 2 to 2, and so on. So we say that F power 5 sends 1 to 1, 2 to 2, 3 to 3, and 4 to 4, 5 to 5. That means F power 5 is nothing but I, the identity permutation. Okay, so in general, we define the order of a permutation. In general, we define the order of a permutation G in Sn to be the smallest positive integer R or such that G power R is I. In other words, the order of G is the smallest number of times we have to do G to send everything back to where it came from. Okay. Now, orders of the permutations are easy to work out using the cycle notation. Now, we gave a few lines above the order of a 5 cycle is equal to 5. And similarly, that for any positive integer R, the order of an R cycle is R. When an R cycle just means a cycle of length R, right? Now consider a permutation. So let's consider a permutation G as it. So consider G, which is a permutation 2, 4, 3, 1, 6, 5, 8, and 7 is fixed in asset. Now to raise G to power R, we get R power R is what? I. So to get G power R is I, we have to make R a multiple of 3 to kill off a 3 cycle, and also a multiple of 4 to kill off a 4 cycle. So R must be at least 12. So you can write that. So to kill off R must be a multiple of 3 and 4. So R is 12. So you can say, so as it doesn't matter which order we write the disjoint cycles of G. So we see that we can write G power 12. So that means we have to write G 12 times so on, and we will get that 2 power 3 power 12, 1, 6, 5, 8 power 12, and 7 power 12, and that will be I. So it follows that the order of G is 12. The order of G is 12. So let's give a proposition to write this thing in a concrete way. (20.4) say that the order of a permutation in cycle notation is equal to the least common multiple of the length of the cycle, right? The cycles. Now, example. (20.6) how many permutations of order 2 are there in S5, right? You can solve this. So by proposition 20.4, we are saying the permutation of order 2 in S5 are those cycle of shape the order 2 permutations are those cycles which has 3 1 cube, sorry, 2 1 cube, which is a cycle shape. 2 1 cube or 2 square 1. Now the number of cycles shape. The number of cycle shape, number of permutations of cycle shape one cube, we have discussed it in example 20.5, is 5 choose 2, which is 5 choose 2, which is 10, while for 2 square 1 is 5 choose 2 multiply 5 choose 2 multiply 1/2 is 15. So the total number of permutations of order 2. So the order 2 permutations in S5 are 150. Sorry, not the multiplication, but the addition, 25. Okay, so there are many situations in which it is useful to be able to work out the order of a permutation. So here is an example again. So $20.7. So we say that a pack of 8 cards is shuffled in the following way. The pack is divided into 2 equal parts, and then interlaced so that if the original shape or order was 1 2 3 4, the new order is 1 5 2 6 and so on. And how many times must this shuffle shuffle to be repeated before the cards are again in the original order. Now the answer would be that shuffles gives the following permutation of 8 card positions. So the permutation is 1, 2, 3, 4, 5, 6, 7, 8. We are sending 1 to 1, 5 to 2, 3 to 2, 4 to 6, and 5 to 3, 6 to 7, 7 to 4, 8 is fixed. So in the cycle notation, F can also be written as 1, 2, 5, 3, 4, 6, 7, and 8 is fixed. So this permutation is order 3. This permutation has order 3. So the cards return to their original after 3 shuffles. Now things get quite interesting if you consider the same problem for different number of cards. Okay. We will end this part also here. And then in the next one, we will describe even and odd permutations.